Now let me discuss other methods of energy band calculation. One of the earliest methods was what was called the cellular method, and this was due to Wigner and Seitz. So, it is called the Wigner-Seitz cellular method. In this, what one does is a Wigner-Seitz cell is first constructed. Let me tell you what a Wigner-Seitz cell is. A Wigner-Seitz cell is constructed. It is just like a Brillouin zone that we constructed in the K space. The thing is that you take a lattice point and include all the points which are closest to this lattice point more than any other lattice point. Okay? So, that is all that a Wigner-Seitz cell is. So, all you need to do is, if you have a lattice, just as we did before, take a point and draw perpendicular bisectors and include the innermost innermost volume that is enclosed by the polyhedra, okay, and things like that. So, this is in 2 dimensions, this is how you do it, and in 3 dimensions it is a little more complicated, but it can be done. Once you do this, then what you say is the following, that is, the potential close to the nucleus is spherically symmetric. Is spherically symmetric. What you mean by that is the following: the crystal potential is minus h cross squared by, crystal Hamiltonian is del squared plus V of r psi is equal to E psi. Okay. And psi Lm I can define, which are solutions of this, and they depend upon both the energy and the coordinates of the point of the electron. So, this I can write it as y Lm theta phi times R L epsilon comma r. Epsilon is the energy. So, of course, we all know that y Lm theta phi's are the spherical harmonics, and these are given by this thing 2L plus 1 by 4 pi L minus modulus m factorial divided by L plus modulus m factorial raised to the power half times P Lm cos theta e to the power I m phi. And once you introduce this, the angular part is a solution of the angular part of the Schrodinger equation, and you can separate the variables just as in the case of the hydrogenic problem, and what you get is the following: you get 1 upon r squared d by dr r squared d by dr plus epsilon minus V of r minus L into L plus 1 by r squared. Actually, let me put plus, okay, because the centrifugal barrier is what you have, but I think it becomes minus simply because I have taken the first term to be positive, times R L r is equal to 0. R L is just a function of one variable, which is a radial distance. Now, I can say that the eigenstate of my problem, which is chi k comma r comma e which is a solution of the crystal Hamiltonian which is the same as the Hamiltonian that I wrote down here. It is exactly the same, no difference, okay, because B of r is the spherical potential that you have assumed, and I will tell you how the fact that it is a crystal comes about. How do you impose the condition that it is a crystal? So, I can write down chi k of r comma E as a linear combination of over all L and M ALM K psi LM E comma R. So, we actually know psi LM E comma R, but we do not know the energies. Now, if chi k r comma E must be a block state, if chi k r comma E is a block state, then it must satisfy the block condition. Okay, what is the block condition? You have the polyhedra which corresponds to the which corresponds to the Wigner-Seitz cell. So, let me just write one of those. So, in this, if I choose the origin to be somewhere here and I consider 2 points on the 2 opposite faces of the polyhedra, let me call this as R1 and let me call the other point as R2, and if they are related by a lattice translation vector tau, then what we are saying is that chi k comma r plus tau comma E is equal to e to the power I k dot tau chi of k comma r comma E. And I must also have the differential satisfying the similar relationship, which is chi prime k comma r comma E is equal to e to the minus I k dot tau chi prime k comma r comma E, r plus tau, this must have been, sorry. And the minus sign is not there, the minus sign is here. I will tell you why we get the minus sign there. So, now once we know this, then we can say, for example, we had the wave function psi k at R2, this is equal to e to the power I k dot R1 plus tau psi k R1 sorry, UK R1 plus tau. This is another way of writing blocks, block functions, and this is equal to e to the I k dot tau e to the I k dot r 1 u k of r1 is what you would write. Okay, so this is the condition. So if this is the case, we have psi k r comma epsilon is written as sigma over L equal to 0 to infinity, sigma over m is equal to minus L to plus L ALMK times chi Lm epsilon comma r. So if I introduce the first condition, then what I have is the following: sigma over Lm (0 to infinity) m equal to minus L to plus L RL epsilon comma R2 YLM theta 2 comma phi 2 minus of e to the I k dot tau R L M epsilon comma this is R2 and this is epsilon comma R1 YLM theta 1 phi 1 times ALMK should be equal to 0. So this is the first condition. The second condition is, supposing I say that I am taking the this thing derivative which is perpendicular to the planes on which these vectors R1 and R2 are residing, then this will be nu 2. So I will call this one as nu 2, which is actually a unit vector, and the other one which is perpendicular to this face, which is also an outward normal, as nu 1. So both nu 1 and nu 2 are outward normals, and I want to find out what the differential of the functions along the direction of the outward normal. So that is actually given by the following, that is because of the continuity of the wave function, I must have nu 1 dot grad psi k comma r1 should be equal to nu 2 grad psi k comma r2. So this is for the continuity in the first derivative, because you want the wave function, according to our basic postulates of quantum mechanics, the wave function should be continuous in value and slope at every point. So nu 1 dot delta psi r1 is equal to, so what it actually means is the following. So this one is nu 1 dot I k times e to the I k dot r1 times u k r1 plus nu 1 dot grad u k r1 times e to the I k dot r1. This should be equal to, the condition is that this should be equal to nu 2 dot I k times e to the I k dot r2 u k r2 plus nu 2 dot grad u k r1 r2 rather e to the I k dot r2 but we know that nu2 is equal to minus nu1. So, for example, we know nu2 equal to minus nu1 because the two are on parallel faces, but facing in opposite directions. Because they are on parallel faces and facing in opposite directions, the two will be opposite, and we can simplify this expression by also recognizing that ukr1 is equal to ukr2 and that r2 is equal to r1 plus tau. So, if we use all these relationships, then what we get is another condition sigma over Lm nu2 dot grad RL epsilon r YLM theta 1, this is r1, let me first put r2 here, theta 2 comma phi 2 plus e to the ik1 ik dot tau times nu1 dot delta r L epsilon comma r times, which is r1 actually, and YLM theta 1 phi 1 this should be equal to times AKLM should be equal to 0. So, here we have one set of equations which I call the second set, and the first set of equations were here, which is this one, the first set. So, you have two sets of equations corresponding to the points which are related by a direct lattice translation vector, and then you have an infinite number of boundary conditions. So, these boundary conditions have to be imposed on all the surface points, pairs of surface points in the Brillouin zone. On the, not the Brillouin zone, on the Wigner-Seitz cell, I am sorry. So, if you did this, then it is not practically possible to impose boundary conditions on all the surface points. So, what people did was a shortcut, that is, choose only certain points and impose boundary condition and solve for ALMK. In fact, the interesting thing is that when Wigner and Seitz solved their problem, what they did was very interesting. All they did was impose only one boundary condition. Wigner and Seitz, when they solved the problem, what they said was let RS be the radius of a sphere of volume equal to Wigner-Seitz cell. So, they replaced the Wigner-Seitz cell by a Wigner-Seitz sphere, and they went around and said that we will put the boundary condition that delta psi by delta r at r equal to RS equal to 0, and they used k equal to 0 was the state used, that is the bottom of the band, and like I said, RS will be equal to 3V upon 4 pi to the power 1/3, V is equal to volume of Wigner-Seitz cell. So, that was the simplest one that they imposed. Now, you know, the problem with Wigner-Seitz, the cellular method is the following, that is, you can choose, there is no way you can choose a unique set of points at which you can impose boundary condition. Okay. So, the solutions actually depend on where you impose a boundary condition. The solution is dependent on the choice of points at which boundary conditions are imposed, which is not a very good thing, because for the same problem you can get different solutions which are which means that the solutions are meaningless. So, Wigner-Seitz method, although it was an interesting method, it was not successful. So, then came methods which were based on what are called muffin-tin potentials. These muffin-tin potential based methods are interesting, because what it says is that if you take a unit cell and you have, say, 4 atoms. Okay. So, let me say that you have an atom 1 here and another atom 2 here and a third atom here, and then a fourth atom which is different and maybe here. So, now what the muffin-tin potential based methods used was the following, that is, the potential at any atomic site is spherically symmetric. So, the same assumption that was made by Wigner and Seitz is made here, saying that the potential at any atomic site is spherically symmetric. But what they did not do was consider only spherically symmetric potential. And they said in the interstitial regions, the potential is a constant or 0. So, you will have a 1 by r dependence in this region and rather a spherical dependence only on the coordinate r here, here, here and here, and the coordinate r is from the measured from the center of the nucleus of the respective atom outwards. Okay. And in the region which is all the interstitial regions here, the potential is a constant. So, this actually solves the problem in 2 ways. One is that the basis is better because we use solutions of spherical potentials in the core region of spherical potentials in the core region, and imposing boundary conditions is simpler because the states in that region are plane waves. Now, the question is, how does one go about constructing the potential, spherically symmetric potential, and how does one deal with the basis is the problem that one really faces in muffin-tin potential based methods. So, essentially what we are saying is the following, that is, we have a contribution from all the neighboring atoms. Okay, for example, if I am considering this atom and these are all the neighboring atoms. So, the contribution of the potential from the neighboring atoms to this particular atom is only a spherically symmetric component as viewed from the origin of this point. This is very important, because when you have a spherically symmetric function around two different origins. Okay. So, let us say that I have two positions, and then I have a spherically symmetric function here around this origin and a spherically symmetric function around this origin. But if I view this function from this origin, if I view from this origin this function, then this function does not look spherically symmetric from this origin. Okay. Because and it will have all possible spherical harmonics that are contributing to the potential at this origin. So, what we really require is project only the spherically symmetric part of the potential from center 2, okay, as viewed from center 1. So, the contribution from there must only be some other spherically symmetric function. So that you can add up the two spherically symmetric functions and get the net atomic net crystal potential that is there at this origin due to the one at that origin. And this is something that has to be done, and we will construct I will show you methods of constructing the muffin tin potential, how one goes about doing that. It is quite interesting and simple. It is based on a technique known as the Loudon alpha expansion technique, and we will discuss that in the next lecture, and also we will discuss in the next lecture the augmented plane wave basis sets, and we will carry on from there to the energy band structure calculations using the APW method. Thank you for now.